Okay, so welcome back to this lecture, and we want to now talk about the upper bound lemma in G. So this is the final thing in the course that I want to prove, and then at the next lecture I just apply it in the setting of some card shuffling in the symmetric group. So let's go into the statement of the upper bound lemma using this Plancher's theorem in the general finite groups. So upper bound lemma, so that's the definition, upper bound lemma in G. So in order to get the kind of mixing and everything, we have to talk about this. So the statement is as follows, that for any mu, which is a probability distribution, and for any n in n, we have the following, that if you take the total variation distance to the uniform, then this is at most half of the square root of the following quite long expression. If you take the sum over the dual group of these classes, which are not equal to the 1, remember the 1 corresponds to the trivial representation, and the dimension of the corresponding vector space, and then we have here, we take the Hilbert-Schmidt norm of the Fourier transform of xi to the power n, take the Hilbert-Schmidt norm of that at the xi and take this squared. That's the upper bound lemma. And if you compare it to the case of G equals ZP, this is really at the same place. In that situation, we just use the L2 norm here to actually bound this expression. So now we just need to basically have this kind of or the absolute value of this Fourier transform. So now we are replacing it with this Hilbert-Schmidt norm. So now proving this, we just need to use basically the same method that we have already done in the group ZP. We just now need to replace the kind of main things with the machinery that we've done on the representation theory of finite groups. So the proof goes as follows, as in the proof of G equals ZP. So we first use the L1 identity and Cauchy-Schwarz. So these two are used in the same way that, remember that in the proof on the ZP case, we took this equals lambda and we took this square. So we always started from this, we square both sides and multiplied by 4 to get it into an expression maybe where we could apply the L1 identity. Then by using the L1 identity and Cauchy-Schwarz, we get actually the cardinality of group in the times the L2 norm of this expression. So if we take this 2, so this is now in the L2 norm this expression. So in the case of ZP, we just got the P in here, so that was the cardinality of ZP. And now in the case of, now we need to apply the Fourier transform, so with by Plancher's theorem. We obtain the following, that now this expression that we want to understand, this L2 norm, n, remember that Plancher's theorem is saying that you can kind of transfer it into the notion of L2 norm. So what we have here is this is equal to 1 over G. Remember that this was the without the square root, so this is just x. And then we sum over the dual group G, and you take the dimension of the vector space Vxi, and then you have the Fourier transform of the convolution. We haven't done anything for it yet. And then we have to subtract this. This is actually because the Fourier transform is a linear operator, so we can write this in this way. So this is the Hs and Xi. That was the Plancher's theorem, that we take the Hilbert-Schmidt norm at Xi to get this expression. So that was the Plancher's theorem. And now the final thing is to notice that if you remember that the trivial representation, so if this xi is equal to 1, so we are corresponding to trivial representation, we have now this psi xi, if you take the Fourier transform, we know that this is equal to the identity matrix, so this is always equal to the identity representation. So it's a trivial representation, so everything is acting with the identity matrix. So this was the identity in this corresponding V1. But this is because it's also the same for the Lebesgue measure, so or the uniform distribution, we have this. So this at the point 1, so now we know that this corresponding mu star n at 1 minus lambda 1, and it's Hilbert-Smith norm at psi, actually in this case it's 1, this is just equal to 0. So we can rule out that term. And if this psi is not equal to 1, so that's the kind of expression we are studying, if you remember, if you take the uniform method, we had already a formula for this, that this is equal to zero matrix. This was what we did in the early on in the previous lectures, in the last week actually, that if you take the uniform distribution, it has this is the zero matrix. So that implies, but because you have a zero matrix, then you just don't need to multiply, you multiply subtracting a zero matrix, so then you get as the expression that this the claim follows. So you can get actually this this expression into this form, that we have now proven that the statement equals to what we had above here, where you take psi not equal to 1, and then you have this of this hs psi no. And now the final thing, in order to make this kind of work in a proper way, actually there's I just noticed that Plancher's theorem, there's one thing missing. There should be a square here. That's in the definition of the Plancher's theorem, because I'm squared on both sides. I just realized there needs to be the square. So in here you have a square as well. So now to complete the proof, we use the convolution theorem for the iterated convolution, which gives you the following, that this expression here, mu star n of Fourier transform psi, this is just equal to the power. So if you take the matrix that this corresponds to, this actually is the power of these matrices. So now you get the result. So this completes the proof. This is true for every psi in G. Because now you have this expression once you have the G on the other side, what we started from. If you take the square root on both sides, we have now given the convolution theorem in display, having the square. So now you can see that kind of the idea with this whole thing is that if you go into the statement of the upper bound lemma, so in the case of ZP, we spent a lot of time actually understanding this notion of a spectral gap of the mu. So here is the kind of the same situation, that if you have a mu, then you need to understand when this thing here is decaying, for example. So if you can actually open this up in a way, then basically what you want to understand, so what we want is that if you take the Fourier transform of psi, so if you can actually open the Hilbert-Smith norm in a way, so for example if it's a self-adjoint operator, you want this hs of psi, you want this to be less than 1, which is equal to, remember this is the Fourier transform at the trivial representation, which would be 1. That would correspond to the hs of 1 at the trivial representation. So this would be like a spectral gap of mu. So now we can do a lot of the same kind of theory that we've done in the case of ergodicity and mixing of these random walks by analyzing this situation when this is happening. And of course, like in a more general group, this can be actually quite difficult problem to establish whether you have a spectral gap or not for this mu. And but if you do have a spectral gap, like if you have this property and you have that mu, if you take this n Hilbert-Smith norm hs psi, you get that this is equal to mu psi. Like some examples have shown where you have this, you get this to the power 2n. Then this implies that this d mu, if you take the self-convolution mu to the uniform distribution, this goes to 0 exponentially. as this n goes to infinity. I mean, this is pure just because you have this upper bound lemma, like in the case of ZP, that if you have this being less than 1, so we have this uniform less than 1, so we remember that this set is a finite set. There's only finitely many of these many psi. If you remember that this is a finite set. So then it's basically just bounding this from above by this, we get an exponential rate. But of course, like using this, like optimizing this, how fast the exponential rate and everything really depends on the representations of this finite group. And that's why in the next lecture, which is the final lecture of the whole course, so when we go to the final topic, I want to show that how in the case of symmetric group, you get this spectral gap for certain random walks, which is actually defined in my case. What I'm going to use is random transposition shuffles on the deck of cards of 52 elements. And in that situation, you do get this spectral gap. So you can actually bound these Hilbert-Smith norms in the way that I want to do here. And then you can use the upper bound lemma to get, for example, a rates at which rate do you shuffle and how fast do you shuffle into some uniform state. So that's all for today. Thanks.